So here is a temperature specific volume diagram, and so this one is temperature and specific volume, TV diagram. So this is the projection of a PVT, a pressure specific volume temperature diagram, the three-dimensional diagram we saw, onto a temperature and specific volume plane. For all pure substances of consistent patterns in their behavior. So this sketch 3.3 is using water, and we use water because it's very common, because it's very straightforward, and most things have a very similar type of appearance. So here we have lines of pressures, isobar lines, that go through, and what's happening here is we can see, like, imagine that we have a cylinder and a piston, and we're compressing the water, and so when we're in this completely compressed state, it's 100% liquid water. This represents what is on our chart above as L, this point. And then here we have a two-phase liquid vapor, and this would be between F and G on this chart. So between here and here on the temperature specific volume chart, and then here we're all the way over on S. We're here in 100% vapor. So looking at this chart, we have in this area we have liquid, in this area we have vapor, in this area we have a two-phase liquid vapor, and there is no solid on this diagram. And we have the isobars that, so this is all given pressure. This line is a pressure of 1.04014 bar, and this line is a line of 10 megapascals. It's an isobar, so all along this line has the same pressure, and so on. We have the 30 megapascals and the 22.09 megapascals. This is the critical point, and we can see the critical temperature. The critical temperature for water is 374.14 degrees Celsius, and 220. So this is temperature critical is 374, and the critical pressure is 220.9 bar. 220.9 bar is 22.09 megapascals. So this is the critical point, and the critical pressure of our diagram. And so if we're above the critical point, then you can't have two phases happening at once if you're above the critical point. So generally we don't draw these to scale. You'll be drawing these, you'll be given some properties, and you're going to be trying to draw these diagrams. Okay, let me see. Then, so if we look at the phase change of a closed system, and this is all listed in the notes, and you can go through it step by step, but again, this closed system, if we're all liquid, then we're here where L is on this diagram, and then F and G. So if we're at the, so given these points, F is the saturated liquid state. And you'll see on the tables, we have VF, UF, HF, and those are the saturated liquid state. That means we're at this point in the dome, at where it says F there. G is the saturated vapor state. We use gas and vapor interchangeably, so the G is like gas. So VG, UG, and HG. And those are on the table, and so those would be at this point. And when we're in between there, we have to find an additional value, and so we have something we call X, and that's quality. And all quality really tells us is where we are between F and G. So if I'm at F, so X equals 0 at point F on that diagram, and X equals 1 at G. So we're just looking at a ratio, and you'll see there's formulas that how to figure that out, but really all we are is between these 2 points. You can see though we have if you think about this graph, there's a specific temperature here, not a specific in the sense of specific volume, but a given temperature. So right there it's 100 degrees Celsius. So all the way across through the dome there, consistently 100 degrees Celsius. That doesn't change. But here, if you look at the picture of the diagram here, you can see we're going from the state where we have solely liquid to the state where we have solely vapor. And you have a certain amount of vapor and a certain amount of liquid. And we're someplace between there. And so we need some kind of other quantity to tell us that, because also the temperature is 100 degrees Celsius and the pressure remains constant as well at 1.014 bar. And so we need some other property to help us know what we have here. And I don't know what the temperature is here, but we can see this isobar comes through up here, and 10 megapascals. We can look up on our tables and figure out what temperature corresponds to 10 megapascals or 1 bar, and note what temperature that is. But you can see that the further up in the dome I am, the less the smaller this distance is, F to G. But on the tables there are values for the saturated liquid and the saturated vapor state at a certain temperature and a certain pressure. So, okay, let's see what else. So these are all, this goes through and talks all about step by step through that diagram, talking about the things I've just talked about. So make sure you go and look at those notes. And this talks about when you're above the critical line and below the critical line, and it step by step takes you through it. And again, here is a phase diagram for temperature and pressure for water. It's not to scale, but the book goes very clearly through all of these, this information. We have this table, this picture, and I think this is figure 3.8, and we can just talk through this again, noting the different points we have. Our critical point is here. Our critical point separates the saturated liquid line. So this line is saturated liquid. From the saturated vapor. So this line is saturated vapor. And the critical point is tabulated, and we can find that. Again, for water, the critical temperature is 374.14 degrees Celsius, and the critical pressure is 220.9 bar. And that corresponds to this critical point here. If we're in the region over here, anything on this side of the dome is vapor, and anything on this side of the dome is liquid. And again, these points are F here. Think of it as fluid is saturated liquid, and here gas, the saturated vapor end of the dome. So at this, the right end here, where the G is, then we've come across, and our cylinder is now full of vapor, or at the border between when it goes from having any liquid left to having only vapor. And an F here, we go from being all liquid to becoming the start of becoming vapor liquid. Vapor liquid two-phase. Again, in the dome here, it's called the vapor dome, but we call this the two-phase liquid vapor. Is what's in this dome, or the vapor dome. Vapor dome. So when you're in the dome, you have two phases, liquid and vapor. And when you're outside, you're one side or the other, you have vapor or liquid. Using our tables, we'll go through some other examples. There's a handout that's called the STEAM table process overview, and that really gives you guidelines for how to go about using the tables. Sometimes we go to the table and we find our value isn't exactly on there. There's one above or there's one below it, and we're in between two. So we have to do something called interpolation. And interpolation, we use linear interpolation in this book. The values are given such that you can use linear interpolation. That just means the relationship between two values on the table are linearly related. And essentially, all we're doing here is a simple proportion to find out where our value is. And I just so strongly recommend you spending some time figuring this out. Find a method that works for you. Use it, practice repeatedly so that you can do interpolations with ease. This is something that comes up over and over, and you should do it eventually without thinking. I'm giving you this a little algorithm here to use if you want. It's the way that I do this, but you can do it however you want. This is saying that this is AB, and then I have a point here, and this would be CD. So perhaps this is temperature and pressure, something like that. Pressure, temperature, in my next example. However you want to look at it. And then this is a line connecting these two. And we're saying that where we want to find this is somewhere here. This is we know X, and we're looking for Y. So we're given some value here of X, and we want to know Y. In this little example, Y is our unknown. And we're saying we know all the rest. So you're given